Hi Year 12s! In this video, we will look at our trigonometry compound and double angle formulas. First of all, it's important to know what sine and cos are. You probably remember using trigonometry to find either lengths or angles of triangles. When calculating sine and cos functions, we model them using the unit circle, a circle of radius 1. You can see that we have used theta as the variable, which is the angle measured anti-clockwise from the positive x-axis. Of the unit circle, sine theta measures the distance along the y-axis, and cos theta the distance along the x-axis. As theta completes a full rotation, 360 degrees or 2 pi, then the values of sine and cos will repeat themselves. Tan theta is the ratio of sine theta over cos theta. This can be seen as the gradient of the tangent on the unit circle. However, it is only positive in the first and the third quadrants. The other important property from the unit circle is if we use Pythagoras' formula for a hypotenuse, a squared plus b squared equals c squared, we get the equation of sine squared plus cos squared equals 1, the length of the hypotenuse. Now, we will look at some of the properties that we need to know when solving trigonometric equations. There are many symmetry properties which can be found in your textbook, so we will just look at the main negative angle symmetry properties. Cos of negative theta is the same as cos theta, as it measures the distance along the x-axis, which is positive in the first and fourth quadrants. Sine of negative theta equals negative sine theta, since sine function is only positive in the first and second quadrants. Tan of negative theta equals negative tan theta. Since it is the ratio of sine theta and cos theta, we know that sine theta becomes negative and cos theta remains positive. We can see from the symmetry in the unit circle that sine theta is just cos theta offset by 90 degrees, or pi on 2. And even more so if you look at sketches of the function. Pi on 2 minus theta is the equivalent of starting at the positive y-axis of the unit circle and moving anti-clockwise, which simulates offsetting the functions. Therefore, sine pi on 2 minus theta is equal to cos theta, and cos pi on 2 minus theta equals sine theta. Now we will look at addition formulas, which are used to model the addition of known sine, cos, and tan exact values to find the unknown value. Here are the addition formulas, and they need to be known in order to complete questions speedily, and are not supplied on the formula sheet. We don't have time to run through the proof of these formulas, but it can be found in your textbook. Another important concept is double angle formulas, which are used to simplify functions. This can be extremely useful, especially when differentiating or integrating functions. These are found by substituting the value of pi for theta in the addition formulas above, so that they are equal to 2 theta, as we can see here. If we sub in our value of sine squared theta from the Pythagorean unit circle earlier, we get the following. Otherwise, we can substitute in the value of cos squared theta from the same Pythagorean identity, which you can see now. We can also do the same double angle manipulation of sine, which, again, is now on your screen. Finally, we can do the same with our tan addition formula. Let's look at an example. We will try some function manipulation in order to simplify our differentiation. For the function shown, let's find f dash of x. Hopefully this looks something similar to one of the double angle formulas that we were looking at before. But first, we need to do some manipulation of the original equation by taking out the common factor of x to get f of x equals x times 1 minus 2 sine squared of 4x. Now we can sub in our cos of 8x for the 1 minus 2 sine squared of 4x. Now, let's differentiate the function using the product rule, where we choose a value of u and v to differentiate separately. Let u equal x, and therefore u dash will equal 1, and let v equal cos of 8x, and so v dash will equal negative 8 sine 8x. Using the product rule, we can see that we end up with the following. Through the use of the double angle formula, we were able to simplify a very complex bit of differentiation. If any of those differentiation steps seem confusing, please have a look at some of our differentiation videos. Thanks for watching and happy studying!